this lecture we want to recapitulate our voltage and current mode control implementation using Matlab. So here I want to recapitulate our customized model development, and this I will be referring frequently to our previous NPTEL course where you can get the detailed material. Then we will recapitulate fixed frequency analog voltage mode control as well, and also current mode control implementation. And then we will recap the constant off time analog current mode control and constant on time analog current mode control. So first we will take the buck converter voltage mode control. So here this is a conventional buck converter. It can be a synchronous buck converter also, and we are talking about a voltage mode controller. And we know about the sawtooth waveform and the control voltages compared to the sawtooth to generate the duration. How does the Matlab file look like? So this is the overall structure of this system, and if I go to Matlab, so let me go to the Matlab. Now this is the Matlab block diagram of this voltage mode feedback control of a buck converter. Here this is the power stage, that means the power converter, and if you go inside, then there is switch node voltage, inductor current dynamics, then DCM enable logic, then the capacitor dynamics. And this accept the input voltage where we can also apply a step input voltage. And here is the DCM enable logic. If it is set to 1, it will become a conventional buck converter. If it is 0, it will become a synchronous buck converter. Then here is the load current. So here we are talking about two type of load. One is the resistive load, that's why it is 1 by R, which is connected between output voltage to this load. Another is the step current load. So you can create a customized load profile so that we can get load transient response. And this is a reference voltage, then we can reference voltage and nominal reference voltage, then we can apply reference step transient. And here we are logging all the data into the workspace, we are saving, and then this is a feedback controller. So let us go to our presentation. So this is the overall diagram that I was showing. Next, if you go inside this converter, the power stage I have shown you the switch node configuration, then inductor dynamics, then DCM logic, and the capacitor dynamics. How does it realize? That means if you take the switch node voltage, it is Q V in minus IL R1. R1 is this one. Then 1 minus Q minus Vd IL Rd. So Vd is the diode voltage drop, Rd is the diode resistance drop. And this can be implemented by means of this logic, and we can create a DCM enable logic like this. Similarly, if you go to inductor current dynamics, we can write dIL dt 1 by L, and this particular term is actually incorporated to enable the DCM operation, and it can be realized by this, and you can get the complete block diagram using this architecture. So this DCM enable block, that means we have a DCM enable. If we set it 1, then it will enable this DCM block depending upon whether the inductor current is touching 0 or not. But if you set it 0, then it will not actually, the inductor current can go to the negative direction, because this always will be 0. That means the DCM enable logic is disabled, and this is the overall block diagram for the DCM enable logic. And the conventional buck converter, if you take the capacitor dynamics, then the capacitor voltage, capacitor dynamics, output capacitor dynamics dVc dt can be written like this, and this is the output voltage in terms of capacitor current and the capacitor voltage, and you can get the complete realization. So the complete conventional buck converter, you can get this detail in this NPTEL online our previous lecture, in lecture number 4. So here we are not again wasting time to again explain the all details of this power stage architecture, but this represents the complete block diagram of this converter. Here is the inductor dynamics, and that include the DCM. This is a DCM enable logic. This is the capacitor and the output voltage dynamics, and this is the switch node voltage. So this corresponds to this block, then this corresponds to this block, then DCM enable corresponds to this block, and this corresponds to this block. So all detail can be obtained in this lecture number 4 of this NPTEL course. Now, if we talk about the voltage mode control simulating diagram, so this is what we are going to consider. In this diagram, what is inside? Inside this controller, that means you are taking the reference voltage and the output voltage, and this is the error voltage, and this is the controller which is GC, and we will program this GC from outside. That means the transfer function, what will be the poles and zero, that will program from outside, right? Or you can realize inside also, there is no problem. Then here it is the ramp voltage, and along with ramp we are considering input voltage feed forward. So if you remove the input voltage feed forward, then this terminal can be simply connected with this ramp if you bypass the input voltage feed forward. And why it is used? Because we have discussed in our earlier course that input voltage feed forward will help to overcome the supply, the audio susceptibility problem or the line regulation problem in voltage mode control, because that is the one of the problem. Because we know in voltage mode control the loop gain is input voltage dependent, and that's why it will suffer from poor line regulation, and that can be overcome by input voltage feed forward, and you can make the loop gain independent of input voltage by this arrangement. Then in this course, in this class, I will also show the Matlab simulation of peak current mode control. How does it look like? So peak current mode control means your reference current, inductor current is compared to the reference current. This is a complete block diagram. You see this block remains same. So this overall this block remains same. We are not touching this block, but only this is going to change. Okay. How does it look like? Here again this error voltage is same. Compensator structure is same, but we may consider a PI controller. Earlier we may consider type 3 or PID. Here you can use type 2 or PI. Then this is the inductor current, and we can add an external ramp, compensating ramp. So this is our compensating ramp, but this is optional. We may or may not use compensating ramp. Then the overall block is compared with the output of the controller. So this is a VCon, and then it goes to the latch circuit. Okay. So let us go to the Matlab block for this current mode. So I will show you, this is the peak current mode control which I was showing. So this block we are going to consider. This is the peak current mode control block I was showing, and if you go inside, this is exactly the block I was demonstrating. So you can get all this architecture. Next, in this lecture, I will also show Matlab simulation of constant off time peak current mode control. Again, this block, only this is the difference. Okay, everything else is same. How does it operate? Here again it is the error voltage, it is the compensator. So this part is common, and here is the inductor current. But after this comparator, this whole logic is different. In fixed frequency we had a latch circuit, but now instead of latch we have a monoshot timer, and this is loaded with the constant off time. Okay, because this is inverted logic, and then we need to consider minimum on time, because in all commercial product, constant off time control product, you need to consider minimum on time, and then you can realize the whole block. Okay. So by this we can realize the constant off time, which is analogous to peak current mode control. That's why it is a constant off time peak current mode control. Then constant on time valley current mode control. Again only this block is different, everything else remains same. How is it realized? Again this error voltage part is common, compensator part is common, and this is compared. So this is different. Here again we are considering a monoshot timer which will be loaded with constant on time. Okay, and all these are discussed in lecture number 23 of our earlier course, that means our NPTEL course on control and tuning method. So in this course you will get details of this implementation. So you can just search here. So lecture number 23 you will get the detailed implementation of this. Let us go to the Matlab. So in the Matlab, again, this is what we have discussed earlier in our earlier course. So I am just summarizing that here we are considering a buck parameter stage. So these are the parameters values. Then we have a buck converter control block, that means where it will call the parameter file, it will load the parameter file. You can customize the input voltage that you want. You can customize what is my initial load resistance value, reference voltage, modulator gain, that means if you want to set the ramp, the maximum voltage is 10 volt. If it is FM, 1 by modulator gain. Then PID controller. In this particular class, I am not going to design controller. I am just taking some arbitrary value of PID. And we know that PID controller, practical PID controller, actually have a time, that tau d, okay, and that we discussed in our earlier lecture. So I have just taken some values, and then you can compute the numerator and the denominator as well as the controller transfer function. Then there are many options. The same controller can be used for many options. One, I can simply use a voltage mode control. The one, I can use peak current mode control. I can use peak current mode constant on time control. I can use valley current mode constant on time valley current mode control. So all these possibilities are there. Only for constant off time control, you need to specify what is my nominal off time, and I have said it is 1 minus d into t. Then what is my minimum on time? For constant on time, what is my nominal on time? Then what is my off time, minimum off time? Then you can accordingly select. Here we are going to simulate for totally 5 milliseconds, and I am applying a step after 2 milliseconds. Then I am taking a load transient of 20 ampere. You can also consider input voltage transient or the reference voltage transient. Then I am calling this buck converter simulation file. What is the buck converter simulation file? If you open this file, you will find I have set DCM enabled to 0, that means it will operate in a synchronous mode. I have considered the initial current of the inductor value, inductor current, and initial capacitor voltage. Then it will ask for the file name. I will simulate the simulating file from the matlab.m file, but the name of this simulating file depends on what preference you are giving at the outside. That means if you say the simulation enter file name is here, which option are you selecting? Are you talking voltage mode? Are you taking current mode? Are you talking about constant off time or on time? So you can simply configure, and this will come here. Then after the simulation is over, all the data are stored in the workspace, and we are calling back all this data, inductor current, ramp voltage, output voltage, and control voltage, and we can plot it according to our requirement. Now you will find here also there is only plot buck. So if you go to the plot comment, we are using subplot, two plot, plot 1 and plot 2, two subplot under one figure, and we are plotting inductor current, and these are the setting. So we'll provide this maybe in another presentation, maybe a tutorial presentation, how to plot it, all the step by step guideline will be given. But in the current lecture, I want to make sure that this thing whatever I am showing, if you want you can plot it, or you can plot separately. It is just the plotting the inductor current data. So one subplot will be inductor current, the other subplot will be output voltage, okay, and then I am linking using a link access so that the two subplot can be linked, and so that if you zoom, both of them can be equally zoom, okay. So let us run the first option 1, that is a voltage mode control. So if we run this voltage mode control, so let us see, we are trying to see that load transient performance using voltage mode control in a synchronous buck converter, and this is the load transient performance. You can see this is the inductor current and this one is the output voltage, and here I am showing it is using a PID controller, and this is a transient performance. So how I am designing, I have taken some ad hoc value, but as we move forward, when you go to week 5, we will talk about the design methodology, how to design voltage mode control. For analog voltage mode control design, we have already discussed, it is already taught in our previous course, but we will summarize but how to design digital control, that we will discuss. But here for a given parameter value, this is the load transient performance. So you can see if you zoom here, then it will also be equally zoomed here. Okay. The next part is that now we want to compare this with current mode control. So that means we will hold this, we will hold this. The next part, since it is a current mode control, do not require any derivative, so you can simply replace, and now we will select option 2 and we will change the color. Here we will change the color to red, otherwise we cannot distinguish. So let us run. Now we are running using current mode control and it is compared. So you can see the current mode control we have not tuned properly, but it is only a PI controller, not sufficiently high gain. So that's why the response is much sluggish. Okay, but we will discuss how to make the current mode control faster. Okay, so because we are using an ad hoc value of PI value, so if we increase the proportional gain, we can speed up the transient performance. But generally current mode control, we saw in our earlier course that the current mode control behave like a fast order system. So that's why it is kind of over damped response. So unless you do load current feed forward, it will be somewhat difficult to speed up very fast within the small signal control bandwidth. So then we can also plot option 3. So the same controller setting, we can go for constant on time and we can change the color to, let's say, magenta. So now we are changing the color to magenta and let us plot. So here option 3 means we are going by peak current mode constant off time control. So earlier it was a fixed frequency constant on time control, fixed frequency peak current mode control. Now we are talking about constant off time peak current mode control. You see the response are more or less identical. There is no significant change with respect to the current mode. I am talking about this red and magenta, they are more or less same. But the voltage mode control is different because we are using a PID controller, and we have discussed earlier that this derivative action is set in such a way it will look like we are providing sufficient damping. So it will act like it is retaining some information of current and load information in voltage mode control. But we are not discussing about the design procedure here, but for the time being let us say this is how the three methods are compared. And the final method we want to compare the option 4, that is the constant on time, that is the valley current mode control, constant on time valley current mode control, and let us use a green color. And it may be expected that again the response will be more or less same like a current mode control. All 3 current mode control, we are using the same controller, they should be more or less same in terms of their transient performance, but different from. So you can see the transient response of all these 3 control techniques are more or less same, not fundamentally very different unless you tune it properly. Okay, so you can see, but their modulation techniques are different. That means we have discussed various control technique and their Matlab simulation. So in summary, we have recapitulated Matlab customized model development, we have recapitulated fixed frequency analog voltage mode and current mode control implementation, then we have also presented constant off time analog current mode control, and we have also discussed constant on time analog current mode control technique. So that's it for this lecture. Thank you very much.